Welcome back. I don't have a cool intro, but factorial notation and introduction to permutations needs no cool intro. It is just cool itself. Where we left off was here. So if you don't have your notes in front of you, you've made some grave mistakes. If you do, I'm so glad that you came prepared. All right, we have two more examples of just understanding that factorial notation. And these ones include pretty much only variables here. So let's start off with this guy. So if I'm taking a look at n minus 4 factorial, I know I start with n minus 4. And then I write the number that's one smaller than n. So one smaller than n minus 4 is n minus 5. Now I could continue going and say n minus 6 and n minus 7, n minus 8, yada, 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 all the way to 3 times 2 times 1. But as we talked about last class, is I can rewrite n minus 4 factorial as n minus 4 times n minus 5 factorial. And the whole purpose for me doing that is to acknowledge, hey, look at the denominator. The denominator is already n minus 5 factorial. And if I have that now in my numerator, I can see that these cancel, cross out, and I'm just left with n minus 4 in my numerator as my final answer because there's nothing going on to that n minus 4. The brackets aren't important. So this is my final answer. Easy peasy. We've got one more to go, and then we can talk about solving an equation that has factorial notation involved. So exciting. So let's take a look at that example. This example here, we actually don't have any division going on. So when we talk about simplifying things, we want to see if we can just combine everything together. So before, I want to kind of draw your attention to an older example we talked about yesterday in class. We said 12 factorial can be written as 12 times 11 factorial, or 12 times 11 times 10 factorial, or 12 times 11 times 10 times 9 factorial. But this also goes the other way. If we are started with this, we can go ahead and say, wait, that's just 12 factorial. Or if we start with this, we could say, oh wait, that's just 12 factorial. Because even though I have that 10 factorial, I have all of the numbers above it that lead to 12, all those natural numbers. Same thing with this. This is also 12 factorial. So if I'm looking at this example, yeah, they don't use numbers, they use variables, but the same thing applies. If I have n minus 2 factorial, one bigger than n minus 2 is n minus 1, and one bigger than that is n. So this whole expression can be rewritten as n factorial. We can just combine it to one simpler factorial instead of multiplication with a factorial at the end. All right, those are all of our simplifying factorial questions. Now we are dealing with this beauty. Oh. And this beauty is n minus 4 factorial divided by n minus 5 times n minus 6 times n minus 7 factorial, all equal to 54. All right, so as we go through this, there's really a bunch of different ways that we can tackle this. And maybe the way that we'll tackle it is similar to how we tackled f above. Is really, I'm going to start by looking at that denominator and say, hold up. Instead of writing that as n minus 5 times n minus 6 times n minus 7 factorial, well, that can just be simplified. I'm going to leave everything else as is. But that denominator can just be rewritten as n minus 5 factorial because it has the number value expression that's one greater than n minus 7 and the one that's greater than that one as well. So I can go ahead and say, well, that denominator is just n minus 5 factorial. Now, technically, that really hasn't helped me simplify anything, but I might notice that n minus 4 factorial can be written as n minus 4 times n minus 5 factorial. Oh, hey, check this out. Well, now we've got something top and bottom that's the same that can be canceled out. And those cancels to, of course, give me ones, but the ones don't play a huge role in this position because they are not in the numerator, it's just simply in the denominator. Now I'm left with n minus 4 is equal to 54, and to isolate a variable, I'm going to move that negative 4 over, that minus 4 over. So I'm going to get n is equal to 58. And that is it. So when we're solving for this equation with n that involves factorial simplification, really the dream is just to simplify as much as you possibly can. Right? So start by simplifying factorial, see if anything can cancel out. Once you end up with that cancel out piece, you can find that maybe the rest of it is just reverse BEDMAS and simplify or solving for that unknown, just like we did here. Okay, we are going to now talk about how to input factorials on your calculator. Because if I had a number, and let's just say, for example, 10 factorial. 10 factorial we know is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we are totally welcome to plug that into our calculator as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But at what point is that going to be too much for you to want to do? Like, are you still going to want to do that if I asked you to determine 37 factorial? What about 98 factorial? I genuinely hope not. That would take you a lot of time. So, specifically, if I want you to calculate what 10 factorial is, there's a way to do that on your calculator. I'm going to show you a sequence of photos of what my calculator looks like when I plug that in. As you look at my photos, which I'm going to pop on the screen in just a couple of seconds, please follow along with the instructions on your sheet of paper in front of you. I will walk you through the first instruction, and the example we're going to do is 10 factorial together. So, the first things first is you are going to type in that number that comes before the factorial sign. So in our case, I'd like you to type in 10 into your calculator. It should look like this. Oh, so beautiful. Okay, your next job is you are going to hit the math button. The math button is located where my finger is in this photo. When you hit the math button, this screen will pop up. You are going to use the left and right arrow buttons to scoot your way over, so in that top kind of row, instead of math being highlighted, you have PRB being highlighted. Pew. PRB stands for probability, because all of permutations that involve factorial notation, all of that is a means to calculate the probability of things or events occurring, so scoot over to PRB. Once you are there, you might notice that that fourth option has the factorial symbol. Pew! You can hit the number 4, and it'll auto kind of select that factorial button notation. Or you could scoot down with those downward arrows and then hit enter. Once you've done that, pew! Your screen should look like this. It'll have the number you inputted, which was hopefully 10. And then a factorial notation after it, that explanation point. Please hit enter. Once you've hit enter, you should get this number. 3,628,800. Now, just for kicks and giggles here, can you please multiply 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 in your calculator? Did you do it? I hope so. And hopefully when you did it, you got that same number value so that you can really trust that factorial notation is not out to fool you. And it will actually calculate it in your calculator for you. So that is that shortcut. back to our regularly scheduled programming. Now that we know how to do factorials in our calculators, we are more than able to go and backtrack and do some of the previous questions like this guy here. I can very easily plug this into my calculator and say 12 factorial divided by, if I'm doing this as in my calculator, I need to make sure that my denominator, since there's multiple things going on, are kept in brackets. So I'm going to go 12 factorial divided by open bracket, and then go 8 factorial, and then 4 factorial immediately next to it. Close that bracket, and I should also get that same answer of 495. Really, the dream. So this notation can help us double check our calculations if I ever ask you to show things by hand, so that if you were to do something like this, you can confirm all your answers are correct. All right. Now, the whole reason that we are using factorial notation is to really just pursue our dreams of calculating permutations. And you may not have known this was your dream, but trust me, it was. Now, permutations are a fancy word that I've been using a decent amount, so let's define it. A permutation is an arrangement of distinguishable objects in a definite order. So when we arrange things, we are placing them in order. What is coming first in that order? What is coming second in that order? What is coming third in that order? So that's what the arrangement implies, and the fact that it is in a specific order. Now, the word distinguishable implies that all of the objects are different, and like noticeably different. So if I had a stack of, I don't know, dinnerware that I got from IKEA, where I get 8 perfectly crisp white plates, and as a prank, someone sneaks into my house and rearranges the plates, I'm not going to notice the difference. Your prank wasn't that great. Because the objects weren't distinguishable. They looked the same. But if you snuck into my house and then, took a plate and a bowl and a small plate and a saucer, and a fork, and you put them all into a weird arrangement, I'm not saying the prank's better, but I'm saying that the prank is noticeable now because each object is distinguishable. Okay? So in a permutation, the key thing is that order matters. And it matters a lot. An example of some permutations would be, let's say I have, for example, 2 students. Maybe 2 students with a birthday that was recent and a birthday coming up soon. And maybe those students are Alyssa and Sarah. I don't know, names I came up with at the top of my head. So imagine you would like to arrange Sarah and Alyssa in a line. And this arrangement, that order matters. Maybe the first person gets a cake and the second person gets a high five. Equally desirable rewards, but the order matters. Okay? Well, the possible permutations would be that Sarah is first and Alyssa is second, or Alyssa is first and Sarah is second. Those are 2 separate permutations because there are 2 separate orderings of these individuals. Okay, we're going to take a look at some examples. In the examples, we are going to find that a lot of them will fall into the category of the fundamental counting principle. And remember, for the fundamental counting principle, we said we would draw lines. And the number of lines that we draw depend on the number of choices that we have. In permutations, we will still have those choices. And on those lines that we drew that each represent a choice, we are going to put the number of options that are available for each choice on top. And because we want to do all of these choices, make all of these choices, it's an and situation, we are then going to take all these numbers and multiply them together. So let's take a look at the first example. So please imagine at one point that there are 6 students in Miss Thibodeau's grade 11 applied class. If there are 6 distinct spots they can sit in, how many possible ways are there to order the students in these spots? So ways that I know that this is a permutation, first and foremost, it asks me how many ways I can order the students in these spots. And as maybe we have recalled, the order matters, which implies a permutation. But I also know that I have 6 distinct spots, right? If I made you sit in different chairs around the room, you would notice a difference. So let's pretend I have 6 spots. So I'm going to draw 6 lines. And you don't have to write this underneath, but the first line could represent spot 1, the second line represents spot 2, the third line represents spot 3, fourth, if you could imagine, would be spot 4, then spot 5, then spot 6. Now, I need to put all of these students in all of these spots. 6 students, 6 spots. So if I have to pick out of my class a student to go into spot 1, I have 6 students to choose from. It could be any of the 6. So I have 6 options for students who could sit in spot 1. When I'm trying to figure out how many students could possibly sit in spot number 2, well, now there's only 5 students left to choose from because one of them is already sitting in spot 1. So I have 5 options of what students could sit in spot 2. And then in spot 3, I've already put 2 students in seats, so now I only have 4 students left. Then I have 3 for spot 4, or 2 options for spot 5. And process of elimination tells me I only have 1 student left to put in that last spot. Because I need to put all of the students in all of these spots, I have to do all of these things. It is an and situation. I have to put a student in spot 1 and spot 2, and in spot 3, and in spot 4, etc. So I'm going to multiply these together. And hey, look, 6 times 5 times 4 times 3 times 2 times 1. I mean, I guess I can plug that into my calculator like a peasant. Or I could plug it in using factorial notation. Don't we love a full circle moment? I do. Well, 6 factorial, try plugging it in into your calculators. Are you doing it? Wicked. Hopefully you did it, and hopefully you got 720. Now, question asks, how many possible ways are there to order the students in these spots? So I want to say that there's 720 ways I can do that. Pew, 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 pew. And that's my final answer. Now, not all permutation questions that we're going to deal with are going to have this like beautiful factorial number answer to plug in. So don't just be like, oh, look at the next question. I see 10 students. I bet the answer is totally going to be 10 factorial. Joke's on you. That would be wrong. So don't get carried away too much. But we'll take a look at the next example. So in example 4, there are 10 students in a dance class, and a teacher must select 3 students to perform in one of 3 different solo spots of their chosen song. How many ways can the teacher select the students to perform in the solos? Okay, so if we're taking a look at this situation here, I have 3 choices that need to be made. Solo number 1, who's going to perform? Solo number 2, Who's going to perform? Solo number 3. Who's going to perform? And again, I can go ahead and label these lines as solo 1, solo 2, solo 3. And I'm probably going to do that just for the beginning questions that we tackle in this section. But just understanding what the lines represent is going to be useful. Now, I only have 3 lines here, but I have 10 students to choose from. So not everyone's going to get a solo. If I'm trying to look at how many options I have for solo 1, well, for solo 1, I have 10 students to choose from. So I'm going to put a 10 on that solo 1 line. Now notice the question says that I have to select 3 students, which means I'm not going to select the same student 3 times. So when I'm trying to choose solo 2, who's going to perform in that, I don't have 10 options because a student has already been taken out of the running. So my next amount of options for solo 2 is 9. I could only choose from the remaining 9 students. And after I choose soloist number 2, I only have 8 students remaining. Now here, my answer isn't a factorial. It's 10 times 9 times 8. And that's okay, because I didn't want you to think that we could always use factorials all of the time. And the easiest way to plug this into my calculator is to simply go 10 times 9 times 8, which happens to also be 720. But just know that if I do get to a permutation type question where I go ahead and I can plug that in for a permutation, I get a factorial notation, I can plug that into my calculator instead of typing out all of the numbers multiplying together individually. So that's the advantage of factorial notation. Not useful 100% of the time, but will help things a lot of the times. Now, things to keep in mind. I wouldn't want to make a graphic organizer for this. This would be awful. Like, I can't imagine wanting to draw a graphic organizer that starts with 10 branches. And then from each of those 10 branches, I draw 9 branches. And then from each of those endpoints of those branches, I draw 8 branches. That would be ridiculous. So the fundamental counting principle can also help me figure out things for permutations. So that's a really great situation. All right, last example that we have. There are 7 staff members to be honored at a retirement party. Alan, Barbara, Corey, Darlene, Ellen, Francine, and Gregory. All 7 of them will be seated at a head table at the front of the room. How many ways could you arrange the honorees at the head table? Oops. So there's 7 people. We're going to assume that there's 7 spots for them. So here's spot 1, 2, 3, 4, 5, 6, and 7. Now, if I wanted to arrange all of these people in spot 1, which is that first line, I have 7 choices. I could choose any of the 7 individuals to sit there. Once I've chosen my person for spot 1, spot 2 now only has 6 people to choose from. Then spot 3 is 5, 4, 3, 2, 1. This particular question ends up with factorial notation. I can plug in 7 times, 6 times, 5 times, 4 times, 3 times, 2 times 1 if I want, or I can go ahead and calculate 7 factorial. And that's going to give me 5,040 ways to arrange these 7 individuals at the head table. Now, permutations are great, but sometimes we have conditions. So say, for example, I wanted to arrange these 7 people, but they're retirees and Gregory's got some preferences. Maybe he's losing his hearing in his left ear. So he goes, I need to sit at the very left end of the table so that everyone is on my right so I could hear everyone a little bit more clearly. So Gregory's got some requests. So we still need to arrange all these people in these 7 spots. But Greg's like, hey there, pal. I need to sit over here. This is where I need to be. So please accommodate my request. And we're like, you know what, Greg? You worked for the company for so long. We're honoring you at this retirement party. Whatever you need, pal. We'll do it for you. So we got to put Greg there. Now, Greg has now added a condition to our permutation. And anytime we have a condition that is irregular or apart from ordering or arranging something, we will always deal with those first. And Greg, our friend, has to go on the far left, and there's actually only one way to put Greg on the far left. And that's to say, hey, Greg, please sit here at the far left. That's it. No other people can go there. Alan can't sit there if Greg's sitting there. It's just not how it's going to work. So we start with Greg, he goes there, and then now we figure out everybody else. So in spot number 2, we still have 6 people left to choose from, then 5, then 4, then 3, then 2, then 1. So by Greg having to have a specific location to sit, we're left with 1 times 6 factorial, which is really just 6 factorial. And if you remember, we've actually calculated 6 factorial 3 times in this lesson, and that answer is 720. So there's 720 ways that we can now arrange these retirees, honorees, honored retirees, at this table if Greg has to sit on the far left. Now, it's possible to have more than one condition. So again, we're going to do the whole same thing. We were getting all the place cards set up, and Greg, we already knew, has to sit on the left end. But Ellen's like, you're losing your hearing in that ear. I'm losing my hearing in the other ear. I need to sit on the far right. And we're like, again, Ellen, you've done so much for this company. We could at least sit you in a place where you can hear other people that day. And so we're like, sure, no problem. Greg will sit on the left. There you go, Greg. And Ellen will sit on the far right. And just like before, there's only one way for Greg to sit on the far left, and that's to be like, hey, Greg, pop squat. Enjoy your spot. And same idea with Ellen. There's only one way for Ellen to sit on the far right, and that's to be like, hey, Ellen, please find your seat here at the far right. Now we have 5 people left, and there's 5 spots left, so the first spot remaining will have 5 options to choose from. Then there will be 4, then there will be 3, then 2, then 1. So this here is 1 times 5 factorial times 1. Or we could see that as just 5 factorial. And 5 factorial, when we plug it into our calculators, try it now. Is going to be 120 ways. So as soon as we add conditions to our permutations, we're going to notice that the number of ways something can happen is going to drastically drop, right? With no conditions, there was 5,040 ways to arrange these 7 people. And then all of a sudden we have one condition and it drops to less than 1,000. Crazy times. So this is our permutations. There's going to be homework that follows. Oh, hey, look, there it is. Question 1 and 2, 3 and 4 are all just about those the factorial notation that we dealt with yesterday in the beginning of today's lesson. And the rest is just talking about some basic permutations. Sometimes there are conditions that exist. Sometimes there are not. The idea is if there are conditions, please make sure that you tackle them first. That is all for today. Please complete the practice. Toodaloo!